So today it's a pleasure to talk about what we've been doing in climate change. Much of this work was a collaboration with Will Happer of Princeton. So what we do is we look how infrared radiation or heat goes from the surface of the Earth through the atmosphere to space. So that heat is not generated just by the surface, but also by the atmospheric molecules themselves. Now, most of the atmosphere is just made of oxygen, nitrogen, and argon. Those are transparent to both visible and infrared radiation in large part. We're interested in these greenhouse molecules. They are transparent in the visible, but strongly can absorb many of these infrared wavelengths or heat. And so the important greenhouse gases are water vapor, carbon dioxide, and ozone, and then to a lesser extent, nitrous oxide and methane. I will also be speaking a bit about some of these fluorinated compounds that we've analyzed in the last half year. Now, what I'd like to discuss first is how does this greenhouse effect work? So on the left side, you see a little panel. Here's an atmosphere with no greenhouse gases. So you can imagine the surface. It absorbs sunlight and then it radiates heat. Because there's no greenhouse gases, those photons or heat that are radiated from the surface can go straight to outer space. So the altitude at which the radiating molecules their radiation can go out to space coincides with the surface. It's important to realize that if the atmosphere of the Earth had no greenhouse gases, the temperature of the surface would be about minus 20 Celsius. So the Earth would be uninhabitable. Next, in the middle panel, we have our standard atmosphere. So not just the nitrogen, oxygen, argon, but these greenhouse gases, the water vapor, carbon dioxide, etc. And here I show there are a lot of molecules at relatively low altitudes. And as you go up in altitude, the density of these molecules decreases. Not only does the density decrease, but the temperature gets colder. So at the surface for mid-latitude, the average temperature is about 15 Celsius. If you go up to the tropopause, around 11 kilometers in altitude, the temperature is about minus 50 Celsius. So it's very cold. So if you're a photon, you're emitted from the surface, you don't get very far. Why? Well, there are these other greenhouse molecules, they're radiating and absorbing. And of course, they radiate in all directions, so they can radiate back to the surface. So this is what causes the surface to be at a nice temperature where we can live at. It's only when you get quite high up in altitude that you'll have a significant probability of being able to escape to space. So here we see this dashed green line. This is at an altitude of typically about 11 kilometers. Next, in the third panel, we consider the case of when we add some greenhouse gas molecules. Now, I've tried to indicate that by a little light blue molecule, here a little light yellow, here a little dashed red. It's difficult to see because we don't add that many. Because we've added more of these greenhouse molecules, that altitude at which the radiation can escape to space goes up slightly. If it goes up slightly, that means the molecule radiating space is slightly colder when we've added greenhouse gas than in this standard atmosphere case. Colder molecules radiate slightly less than warmer ones. And so that means there's an imbalance. We get more sunlight than heat is radiated, and this is called a radiative forcing, and this imbalance means that there's going to be some warming. Now, the point I wish to make is as follows. Notice that this greenhouse gas, it only occurred because we had the temperature decreasing in altitude. It was relatively warm at the surface, and then when you go to the top of the tropopause at around 11 kilometers, it's colder. If you had an atmosphere where the temperature was the same, an isothermal atmosphere, there would be no greenhouse warming. Finally, You could ask, what happens if the temperature increased with altitude? Well, then you would get a forcing imbalance the other way. You would get more radiation emitted to space than came in, and that would result in global cooling. Now, what does the temperature look like? Well, on the left panel, you see the temperature versus altitude, and this is the result of balloon measurements. So if you go at the surface of the Earth, you go up in the troposphere, you see the temperature decline steadily until an altitude of about 11 kilometers. Then the temperature levels off, and in the stratosphere, it starts to increase. Why is that? Well, there's an ozone layer. Ozone absorbs ultraviolet light from the sun. These ozone molecules collide with other gas molecules in the atmosphere, and that means the stratosphere is warming as you go to higher altitudes. Finally, if you go to very high in the atmosphere, in this mesosphere, the density is very low and the dense temperature falls off. In our calculations, we need to know what's the concentration dependence of these greenhouse gases with altitude. That's shown on the right panel. So notice that water vapor, its concentration decreases very sharply with altitude. When things get colder, water basically freezes out. CO2, on the other hand, remains constant. Now, what does this mean exactly? Constant, we all know that as you go higher in altitude, the density of air decreases. A constant concentration means that 400 parts per million of the air at the surface are CO2, as well as 400 parts per million of the air at a higher altitude. The CO2 concentration is always a constant. These other gases, that's clearly not so. Ozone, we see here it increases between 30 and 40. That's where it has its maximum concentration. Methane and nitrous oxide, they decrease with altitude. So it's this concentration dependence with altitude comes from observations that we utilize in our calculations. Now, these greenhouse gases have been increasing as a function of time. Nitrous oxide, this comes primarily from fertilizer use. It has been rising rather steadily for the last 40 years. Methane has a rather strange temporal dependence. It was increasing in the 1980s, and then the 1990s, early 2000s leveled off. In fact, if you look carefully at the measurements, in one of those years, it actually went negative. The methane concentration in the atmosphere decreased. In the last 20 years, we see it has been increasing. Now, I've shown this before to you, and the reason I'm showing it again is I still don't know why the methane concentration leveled off and, in fact, decreased in one of those years from about 1995 to 2005. The only suggestions I've heard is, well, we cleaned up Russian pipelines. I'm a bit suspicious of that Western superior attitude without showing some data showing what the leakage rates were in Siberia and near Kazakhstan. One possibility that has been mentioned is if the temperature goes up, you have permafrost melting. There's a lot of methane trapped in the permafrost, and that would then release more methane. However, in this time period from 1990s, temperature was going up. So that's inconsistent with this flattening out of the methane concentration. So again, what's going on here with methane in the 1990s, early 2000s? I have not heard of good reason. Carbon dioxide has been going up steadily. These are measurements taken at Mauna Loa. Mauna Loa is far from industrial areas, so you get a pretty good measurement of the global average. And the CO2 concentration has been going up rather steadily. If you look carefully at the curve, you can actually see when there have been these global recessions. I believe a few years ago with COVID, you could see that the CO2 did not increase as fast as it did prior to COVID. Now, when you have CO2 going up, Here are some measurements in the bottom panel at alert. So the CO2 is in this blue panel. The carbon from these fossil fuels burns with oxygen, so you expect CO2 to go up, coinciding with a decrease in oxygen, and indeed there is a slight decrease in oxygen. Note, however, that the oxygen decrease of about 90 parts per million from 1991-2013 is greater than the CO2 increase of about 36 parts per million. The reason is that a lot of the CO2 that's produced goes into the oceans. So that's why these two are not equal. Now, in the last year, we also did some work on these halogenated gases. The two most famous are CFC-11 and CFC-12. These were commonly used in refrigerants, and then it was noticed in the 1970s that they contribute to the breakdown of stratospheric ozone. And that, of course, the fear was that this would allow more ultraviolet light of the sun to get to the surface and cause more skin cancer. So in the late 1980s, there was this agreement sponsored by the United Nations. It's known as the Montreal Protocol. And this sought to restrict a global use of the CFC compounds. And if you look at this plot of concentration versus time, you can see after this Montreal Protocol was implemented in 1989, CFC 11 and 12, these black dots and these red dots, are starting to go down very significantly. Now, there have been a lot of replacement of these refrigerant chemicals, and these have all kinds of names. These chemicals are less harmful to the ozone. They basically break apart a lot faster when they get to the stratosphere. Some of them, however, do have a negative impact on ozone, so there have been amendments to the Montreal Protocol to restrict their use. So there have been a whole slew of chemicals designed to replace CFC 11 and 12, and then there have been new compounds to replace the replacements. Now, the reason why I'm including this slide is that these CFC compounds, in addition to having an impact on ozone, also are greenhouse gases. So people have said, oh, that means they're doubly terrible. But what I'm interested in today is to talk about their greenhouse effect, not the impact on the ozone. I believe they do have a negative consequence for ozone. I support the Montreal Protocol, but today I'm just interested in their greenhouse properties. As it will turn out, the greenhouse effect of these gases is very small, largely because the concentration here is ppt, part per trillion, whereas when we were talking about methane, CO2, nitrous oxide, we were talking about part per million levels. Also, a number of these gases, I had to multiply their concentration by a factor of 10, otherwise you wouldn't even see them on this ppt, part per trillion graph. Now, we have calculated the flux, or the heat radiated per square meter at the top of the atmosphere. And this top panel I'd like to see show the effect of CO2. First of all, if we have no greenhouse gases, we get this blue line. So this is the flux, the energy per area per second radiated for these infrared colors or infrared frequencies. So blue line is no greenhouse gases. The black line is when we put in our water vapor, our CO2, ozone, methane, and nitrous oxide. And then we get this black line. In this region over here, there are a lot of water lines, so that's why the black curve is below the blue curve. And then we have this big dip around 660 wave numbers. This is the big effect of CO2. The second dip, just over about 1050 wave numbers, that's due to ozone. This dip over here past about 1300, this is primarily water vapor. There's a little effect due to nitrous oxide and methane. If we consider only the greenhouse gases without CO2, we get the green curve. So this accentuates the big effect of the CO2. If we double CO2 from 400 to 800, we get the red curve. You don't see much difference. You see a little bit here. So it's the difference between the red curve and the black curve. That's what all the fuss of this global warming business is all about. Okay, now let's go to the lower left panel where we do the same thing, but now we take methane. So we consider a transparent atmosphere, so we get the same blue curve as we did in the upper panel. We consider the standard concentration of methane. I use 1.8 part per million. I think nowadays it's closer to 1.9 part per million. We get the black curve. If I take out the methane, I get the green curve. You can just see a little difference between the black and the green over here. If I double methane, I get the red curve. Again, you have to look hard to see any difference. So you immediately see the effect of methane is going to be much less than due to the effect of carbon dioxide. Next, on the right panel, we have nitrous oxide. So again, the blue curve, transparent atmosphere. Black curve, we put in our standard 0.32 part per million nitrous oxide. And the green curve, no nitrous oxide. Red curve, doubling it. And again, you just see a tiny effect. Notice that the nitrous oxide and methane both seem to affect the spectrum at about the same wavelengths. So they kind of interfere with each other. Now, of course, the question you have to ask is, well, those are nice curves, but why should we pay any attention to you? Well, in science, the way you determine whether you should be paid attention to is you look at observations and see how well do you predict those. So at the top in B, D, and F are observations taken by a satellite. So this satellite measures intensity as a function of the infrared color or wavelength. And the observations are when the satellite looks at the Sahara, Mediterranean in D, and Antarctica in F. On the left side are our calculations. First of all, for the Sahara, notice the intensity goes from 0 to 200 units. That's higher than for the Mediterranean, where we go from 0 to 150. Why is it higher? It's hotter in the Sahara, so it radiates more energy. And of course, when you go to Antarctica, the intensity goes from 0 to 60 units. It's a lot colder, so you get a smaller signal. This red curve, that's that signal that you would get if there were no greenhouse gas, if the atmosphere were transparent to the infrared wavelengths. So this is calculated using the surface temperature. Notice for Antarctica, this red curve is below the intensity signal that you see. And the reason for that is the surface of Antarctica is colder than the air above. Cold air is heavier, it goes down to the bottom. So because the air above Antarctica is a bit warmer, you get a higher signal than you would if you just look at radiation coming from the surface. So the nice thing about these top figures is that we could fit this, we could calculate without needing any fudge factors at all. Now, you can also say, well, do you have to go to space to take the measurements? And the answer is no. You can also put your instrument on the ground, look up, and then you see the radiation coming down at your instrument. And so that's what is done in H and J. Here we had an instrument in Nauru, which is in the Pacific, and Barrow, Alaska. And our model is pretty good. The reason we're less proud of that is we had to use a fudge factor. What is the fudge factor? Well, basically, people look at their model, compare it to the observations, and the difference they say is a fudge factor we're going to add into the calculation. Now, fudge factor is not a very nice name, so they gave it a fancy christening called the water continuum. Now, it's not quite as bad as I've made it sound. Around Nauru in the Pacific, there's a lot of water vapor, so the fudge factor is very big. In Alaska, there's less of a fudge factor because there's less water vapor in the air. Nevertheless, what is frustrating is people still don't understand what's responsible for that water continuum. My own suspicion is that basically what it is, it's some water-induced haze or cloud like smog in the atmosphere. And that is what causes some additional absorption that you have to take into account. Now, if we integrate the intensity or integrate the flux at all wavelengths, then we get what's known as the flux, and we can plot this versus altitude. So as you go up, you're above most of the greenhouse gases, the flux becomes a constant. And you can make this calculation for standard CO2 atmosphere of 400 parts per million, double the CO2 or half it. And there will be a slight change in the flux coming out at the top of the atmosphere. This difference in the flux when you have a normal atmosphere or doubling CO2, this is called the radiative forcing. And for doubling CO2, this flux is 3 watts per square meter. And so the question is, how well does this compare to what others have calculated? And so when we double CO2, we get 3 watts per square meter. Some of the others have gotten 2.8. So we're actually worse than some of the climate folks. Doubling nitrous oxide, we get 1.1 watt per square meter. Others get 1.2. Doubling methane, we get 0.7. Others get 0.6. We've also considered what happens if we increase ozone. In the case of water vapor, if we add 6% of water vapor, that would correspond to, say, a 1 degree C increase in temperature. For every 1 degree C increase in temperature, the saturation water vapor goes up by 6%. We're a bit lower than what others get. But the bottom line here is that our results are pretty much in line with what others get. Now, so far, all what I've talked about is a clear sky. Well, what happens if we have clouds? And we have done some work on that, and I've labeled this as preliminary work because Will said, William, you haven't written that up, and you have to really show me that you know what you're doing. But I feel I do, but I'm busy in writing it up right now. And I think this result is kind of nice. So I'm going to show you this, these results hot off the press. And here we consider the effect of scattering. Now, I think we're all familiar. If you look in a clear sky, it looks very blue. And the reason it looks blue is you get this visible blue light, which is scattered by all these nitrogen and oxygen molecules in the sky. Visible light scatters very well. Infrared light does not scatter well by these greenhouse molecules. The reason is that the scattering depends as 1/4 power of the wavelength. So if you go from a visible wavelength, which has a wavelength of about, say, 0.5 micron, to, say, these infrared wavelengths, which could be 15, 20 microns, this is the wavelength increased by almost a factor of 100. If you then take 1/4 power of that, you see the infrared scattering by these greenhouse molecules is suppressed by more than a factor of 1,000,000. However, if you have a cloud, it can strongly scatter radiation. Now, taking into account cloud scattering is a mathematical challenge. Will and I have worked very hard on it, and recently we think we licked it. So we posted last month a mathematical paper which describes how to take scattering into account, and I've started to apply those results to actually consider cloud layers. So here what I've plotted is the ratio of the forcing at the top of the atmosphere when we have a cloud divided by the clear sky forcing. So if a cloud had no effect, we would just get 100%, the same forcing when we have a cloud as when we have clear sky. And I've considered 3 cases. First of all, for black, we consider a very thin cloud. For people who are a bit technical, the optical depth is 0.1, so we can almost look right through the cloud. In the case of the red, we have a bit of a thicker cloud. Optical depth is 1. And finally, in the case of blue, we have a very thick cloud. So you can think of those as those thick black thunderstorm type clouds. And notice the forcing goes down dramatically. When you have a thin cloud, the forcing is reduced from 100 to about 75%. This moderate cloud, still slightly a positive effect, But for this thick thick cloud at high altitude, we get a negative forcing. Next, we have plotted this versus omega. Omega is given the technical name of single scattering albedo. When omega is 0, you get no scattering. When omega is 1, you get no absorption. So we've done our calculations for a whole range of this single scattering albedo. Finally, when you consider scattering, you don't know if the radiation is scattered in all directions equally. This is called isotropic scattering, or if it is strongly scattered in the forward direction. So we've considered two types of scattering, isotropic and forward scattering. And notice when you have this thick cloud, you always get a negative force. Why is that? Well, let's go back to our temperature slide. Before we considered the temperature at the surface, it went down until the tropopause. And then the temperature went up. It went up because you have that ozone absorbing the UV in the stratosphere. Now, if you have a very thick cloud layer at 11 kilometers, basically the problem is no longer radiation from the surface of the Earth, but it's from the surface of that thick cloud layer, which doesn't let anything from the surface through. Well, if you put the surface right here at 11 kilometers and see what happens to the temperature above that thick cloud, the temperature goes up. The temperature goes up above the surface. You get a greenhouse effect that cools rather than warms. Adding additional greenhouse molecules to a higher altitude means that you get more radiation emitted, and then you get this imbalance that there is more radiation emitted than radiation coming in from the sun. Now, that's very nice, but of course you're saying, well, let's show us the observations that back that up. And here's some observations, again, from that Nimbus satellite. These are observations taken over the Western Pacific. So the top slide shows two curves. First, there is the data shown for a clear sky, and later a second set of data for the same region, but when there's a thick cloud. So when there's thick cloud, we see this bottom line right there. Now for the clear sky, we can analyze that very quickly. So here's the results. My PowerPoint didn't quite come out well when I went to this screen share. This solid red curve really should be dashed, and this corresponds to the brightness at a temperature of 295 Kelvin. This lower blue curve, which should also be dashed, this corresponds to a temperature of about 214 Kelvin. So here the black curve is when we consider a standard atmosphere. A red curve is when we double the CO2, and the green curve when we set the CO2 to 0. So the difference between the red curve and the black curve, this gives our forcing, and this turns out to be about 3.15 watts per square meter. This is a little higher than the 3.0 watts per square meter. We found that other value for a mid-latitude region. Now, when we consider the Western Pacific, we had to consider a tropical temperature profile. It's a bit warmer, and that's why we get a slightly larger forcing. Next, we look at this cloudy sky. Well, sure enough, we can nicely calculate it. Basically, you just see two bumps. One is CO2, which is above the cloud, and the other is due to ozone, which also tends to be above the cloud. I've blown this region up here. If I consider what happens when we double the CO2, we see this difference. But now notice the red curve is above the black curve, opposite the other case. So now we get a negative force. So this does coincide with the measurements I showed you on the previous slide. Now, why are clouds important? Well, at any time, clouds cover about 70% of the Earth's surface. So showing clear sky results is not very realistic when you're approximating the atmosphere of the whole Earth. That's the reason why everyone knows clouds are important, and there's a lot of uncertainty in knowing how to incorporate them in our calculations. And that's why the IPC sensitivity, i.e. the warming that you get when CO2 doubles, really hasn't changed for 30 years. In 1990, they said the sensitivity was between 1.5 to 4.5 degrees. Remained the same until 2007. They said that then it was 2 to 4.5. Then 2014, they went back to the original value. And then a few years ago, they changed it to 2.5 to 4. Not that much progress. Now, this is a tough problem. If we take the clear sky forcing, which is 3 watts per square meter, that's only about 1% of the total heat flux to space. That means you only need to have a very small change in your clouds, i.e. more high altitude clouds, thicker clouds, maybe a somewhat larger area of the Earth covered by clouds, and clouds could easily make up this 3 watts per square meter difference. So this is going to be a difficult problem to measure, to see any change of clouds which would compensate for this small radiative force. And there's this principle that this French chemist Le Chatelier came up with about 2 centuries ago. When you have a system at equilibrium, such as the climate, and you subject it to a small change in concentration, temperature, volume, or pressure, the system changes. It reaches a new equilibrium in such a way that it partially counteracts the applied change. So it's perfectly reasonable to expect that the Earth climate system, that clouds are going to adapt in such a way to compensate for that 1% change in the radiative flux to space. Now, one of the things that I thought I'd better do is talk about the global warming potential. I think this is an entirely useless concept, but it was invented by some people who supposedly wish to compare the effect of these different greenhouse gases to CO2. I don't think it's a very good comparison. I think it's basically an attempt to scare folks by generating some high numbers. It's a bit like if people get a high tax bill, they get upset. But anyway, I wanted to show you that we get similar global warming potential values than the climate community. So the definition is that we find the global warming potential for a gas I for a given time period, capital T. And we first consider the radiative forcing of gas I, and we divide by the column density. So the forcing is in units of watts per square meter. The density is molecules per cubic meter, but column density is molecules per square meter. So if we divide watts per square meter divide by molecules per square meter, we get power per molecule of watts. So we take the power per molecule of gas I, divide by power per molecule of CO2. We also divide by the mass of gas I and mass of CO2. Next, we have this function theta. Theta depends on capital T, the period that you're looking at the global warming potential, and also depends on the lifetime of gas I in the atmosphere. Now, in the case of CO2, it's a bit complicated because there are various processes going on. CO2 goes into the ocean, CO2 goes into plant life, etc. So you actually have to have several exponentials here. Anyway, we've taken this formula and evaluated it. We consider CO2, since everything is relative to CO2, you just get 1. Methane, 1 molecule of methane is 31 times more effective at global warming than 1 molecule of CO2. For nitrous oxide, 1 molecule of nitrous oxide is about 233 times more effective at global warming than 1 molecule of CO2. And then we consider the masses of the molecules, the lifetimes, and then we calculate the global warming potential for 0 years, 20, and 100 years. And this is what are the values in the IPCC a few years ago. They get slightly lower value, or they get slightly higher values for methane. We believe the reason is that when methane goes into the stratosphere, it breaks down, it oxidizes and produces a CO2 and water vapor molecule. Those, of course, are greenhouse gases. So the products of that methane breakdown, they like to include in the greenhouse effect of methane. This is a so-called indirect effect. We did not do that. For nitrous oxide, our values are very close to what people calculate. Now, the reason why I don't think it's a very useful concept is when you go out in the morning, you don't say, honey, what's the global warming potential? Should I put on a winter jacket? And what you really want to know is what's the effect on temperature. So let's look at the projections of these greenhouse gases for the 21st century. Now, we're going to make several assumptions. First, we're going to assume that during the 21st century, these greenhouse gases of CO2, methane, nitrous oxide are going to be increasing at the 2000 to 2020 rates. Why did we pick that 20-year period? Well, you may recall that methane leveled off in the 1990s. So in order to be as fair as possible to the climate community, we want to use very high increases of these greenhouse gases. And that's why we threw out the 1990s, because that would give us low values of the effect of methane. Secondly, we're going to assume that the warming in the 21st century is about the same as in the 20th century, about 1 Kelvin per century. If you don't like the 1 Kelvin, well, make it 1.5 Kelvin, whatever you prefer. You'll still get very low numbers. And we're going to assume that this 1 degree C per century increase is all due to greenhouse gases. And I'll have more to say about that in about 5 minutes. And finally, we're going to use these forcings that come from the clear sky. So we're not going to use the effect of clouds, which decrease the forcing significantly. So here we consider the gases, CO2, methane, nitrous oxide, and these halogenated gases. We use 14 of these halogenated gases that have the greatest greenhouse capability. Here are the concentrations in this year. And then we look at the rate of increase of each gas relative to that of CO2. So in the case of methane, we see that for each 1 molecule of methane being added to the atmosphere, we're adding 312 CO2 molecules. In the case of nitrous oxide, for each 1 nitrous oxide molecule, we're adding over 3,100 CO2 molecules. Next, we look at the greenhouse powers. In the case of methane, 1 methane molecule is 31 times more effective at warming than 1 CO2 molecule. So the net effect of the methane is going to be 1 over 312 times 31, 1/10 warming as CO2. Nitrous oxide, the effect is going to be 233 divided by 3125, about 6% that of CO2. So here are the warmings per century. For CO2, about 0.83 degrees per century. Methane, 1/10, 0.08 degree per century. Nitrous oxide, 0.06 degree per century. And these 14 of your strongest greenhouse gases, of these halogenated gases, about 2%. And you add these all up and get 1. If anyone says you're being too conservative, too optimistic about 1, I think this number should be 1.5. Well, then multiply everything by 1.5. Even doing that, you're going to get very low increases of warming due to nitrous oxide, methane, and CO2. Now, what's the effect of some of the policies being proposed? One of the policies being proposed is to outlaw fertilizer use. Well, I suggest that we be a bit cautious. If you look at the production of various agricultural products over the last last 100 years, you see been this dramatic increase in everything: corn, wheat, barley, hay, etc. And this coincides very strongly with this dashed blue curve, which is the amount of nitrogen fertilizer used. Now, undoubtedly, this increase in crop yield is due to many things: better seed, better farming techniques, but fertilizers is a very important contributor to this increase. So if you're going to outlaw all fertilizer use, you're going to have global famine. So I would argue that outlawing fertilizer use is rather silly, especially since the increase of nitrous oxide leads to a temperature increase of only about 0.06 degrees per century. Now, of course, farmers are intelligent people. Better use of fertilizer rather than having it run off into a stream and cause algae blooms. That's, of course, something that everyone knows is a wise thing to do. So better farming techniques where you make sure the fertilizer stays on your land, benefits your crops rather than runs into streams. Of course, everyone supports that. But outlawing fertilizer, I think, would be a dumb idea. Next, what's the response of vegetation to these increased greenhouse gases? Well, there was this nice experiment done by Professor Idso some years ago. He took a pine tree, put a bag around it with just ambient air. Then he put another tree in a bag, but he added 150 parts per million. Another bag, 300 parts per million in addition, plus 450 parts per million. And you see the tree grew much faster. So this is something every greenhouse grower knows. They add CO2 on purpose to their greenhouse to get the crops to grow faster. But there are other effects. It turns out that when you have more CO2 in the atmosphere, that the holes in the leaves, called the stomata, through which the CO2 enters the plant, they shrink. So it's a bit like having a bunch of noisy teenagers. When you put a lot of food in front of them, they have smaller mouths. Same thing with plants. A lot more food, a lot more CO2, the stomata shrink in size. Why is that important? If the holes in the leaf are smaller, there's less water loss, and the plants can grow better in drier regions. And here's a study shown by NASA, and green indicates where plants grow faster. And noticeably along the border of the Sahara, where it's very dry, plants grow better, and this is attributed in significant part because of the higher CO2 concentration in the atmosphere. Finally, I'd like to say something about temperature observations and the climate sensitivity. So for CO2, the warming, the increase in temperature delta T, is the thing S called the climate sensitivity times the logarithm of the concentration of CO2 divided by the concentration at some earlier time. And this logarithm is to a base 2. Basically what it says, if I double the concentration of CO2, so C is 2C naught, delta T is S. So the question is, what is the climate sensitivity? Well, first of all, let's look at the observations of temperature throughout the last 150 years. So here are some data from 5 different organizations. The data starts in the late 1800s. I suspect this data from 1850 to 1900 is not very good because basically you didn't have many stations measuring ocean temperatures, measuring Antarctic temperatures, Amazon, polar regions, etc. But from 1900 on, it gets pretty good. And we see from about 1905 to 1940, the temperature went up by about half a degree. Well, during this time, the CO2 went from 298 parts per million to 311 parts per million. So if I substitute delta T is 0.5 and these concentrations of CO2 into this formula, I get a value of S of 8. Now, what happened after 1940? From 1940 to about 1980, the temperature declined, maybe leveled off, 0. CO2 went up from 311 to 339 parts per million, climate sensitivity 0. Then from 1980 to 2000, it went up by about half a degree. CO2 went from 339 to 370, so that corresponds to climate sensitivity of 4. And then a big surprise. All the global models thought, oh, this increase is going to continue, and it didn't. It flattened out. This is called the global warming hiatus, from 2000 to about 2016. CO2 went up a lot from 370 to 400 parts per million. No one knows why that happened. And recently there's been a bit of increase. I think this past year was an El Nino, so we've had a warming of temperature. The point is, this climate sensitivity from the observed data doesn't agree very well with the best value of 3 from the latest IPCC. There is certainly a lot more going on to the world's climate than just CO2. The likely culprits to me probably is the sun, probably is ocean currents such as El Nino, etc. And it's probably going to be some complicated combination thereof. And of course, you have to worry about clouds. So conclusions. If we extrapolate the warming of 1 degree since 1850 to 21st century and assume that's all was due to greenhouse gases, which is very unlikely, and use clear sky forcing, so we forget about clouds, which greatly reduce their effect, we get warmings of CO2 0.83 degrees per century, methane 0.08, nitrous oxide 0.06 degrees. This adds up to 0.98. I didn't write down the 2% contribution to the halogenated gas compounds. For Ireland, Ireland produces about a part in 1,000 of the CO2, a bit more than a part per 1,000 of methane and nitrous oxide. So the Irish contribution to warming is very small. If you sum everything up, it's less than 1 millidegree per century, something completely immeasurable. Now, today I didn't talk too much about the effect of droughts, floods, polar ice, glacier retreat, sea level rise, ocean acidification, forest fires. I've talked about that in the past. I did have a reference. This reference talks about Ontario's climate, but there's a lot of data there for the entire world. So, for example, you probably heard the news this summer, all of Canada was burning down. But if you look, yes, we had a lot of forest fires this year, but if you look at the data for the last 30 years, there's no clear trend at all. Similarly, if you look at, say, the polar ice, we started to monitor it in 1979. It retreated quite a bit in the 1990s, early 2000s. Since 2007, the September polar ice is just flat. In preparing for this talk, Will said, William, here's a nice article I found. It was in the climatedepot.com. U.S. farmers defy a scorching summer to grow record crops. So there is a lot of good news going on in the world. The climate crisis doesn't seem to be substantiated when you just look at the data behind these headlines. So summary, outlying fertilizers negligibly affects climate and endangers global food supply. Moreover, I think you need to be very cautious. If you take an acre of productive farmland in Ireland or the Netherlands out of production, you're probably going to have to increase farmland elsewhere. So probably that means that you'll have to cut down a lot greater area than 1 acre of the Amazonian rainforest. So from an ecological standpoint, inadvertently, you may be doing great harm. So the conclusion is that the world is not in crisis, not in 5 years, 10 years, not even 100 years. Thank you.